Okay, so last time we had kind of introduced some of the basics of hemoglobin, and we wanted to get into the discussion of how does oxygen bind to the iron center within hemoglobin. And to do that, we're going to have to do a little bit of molecular orbital theory. Now, if you recall last time, we said a couple of important things. We said that iron is in its +2 oxidation state, which means it's high spin and has a 3d6. And we went back and we just did a quick, brief summary about an octahedral iron center. But for those of you guys who are particularly observant, you'll notice that iron isn't octahedral when the oxygen is not bound to the iron center. Okay? So remember, when we just have an open, right? When we have an open coordination site there on the iron, when we just got the porphyrin, right? The porphyrin and the one histidine, right? We've got a 5-coordinate, right? We've got a 5-coordinate ligand system, right? Which is, in this case, going to be a square pyramidal geometry, okay? Now, it would be a good exercise for you to say, uh-oh, right, this is a different molecular orbital diagram. Could I figure out what the splitting diagram is for this geometry, which we didn't explicitly talk about in class? And your answer is, sure I could. I know how to use Google. I can go look it up, which is fine, right? You know, that's a valid way of figuring something out. But the point being is, can you figure out how the orbitals on the d, let me start over again, how the d orbitals are going to split with a square pyramidal geometry. And it makes kind of logical sense. We're going to have a lot of bonding in the xy planes, right? So the x squared minus y squared and the dz squared orbitals are going to have significant bonding. And so they're going to get pushed up because those are going to be our anti-bonding. The xy is going to have a little bit, and the xz and the yz are not going to have that much. Okay? Okay, so let me translate that into something here, right? So here is the d orbital splitting diagram for a square planar, particularly, right? Something that we can use to approximate what's going on in hemoglobin. You'll count that there are 6 electrons that I have right there in green, right? Those are my 6 d electrons coming from the iron, okay? Why am I showing you guys this? Well, remember when we're trying to construct an MO diagram, I need to know 2 things. I need to know how the d electrons are behaving, and then I'm going to need to figure out the molecular orbital diagram for whatever's coming in. Okay? Now we're bringing in oxygen. So if you'll allow me to pause here for just a second, I'm going to scroll and find the molecular orbital diagram for oxygen, so it should be in your notes also. So I'll see you guys in just a second as soon as I scroll up there. All right, we're back. Okay, so in your notes you should have this also, right? This is something I believe is in one of the previous videos too, right? So go back and take a look at this. This is going to be important, all right? So this is the molecular orbital diagram for oxygen. Remember, we're trying to mix our metal with the oxygen, so we need both of those molecular orbital diagrams. Now, what's going to happen is the highest occupied orbitals here of the oxygen, which is going to be our pi star orbitals, okay? Our pi star orbitals. Our pi star orbitals are going to interact with the orbitals on the metal themselves, right? So we're going to do this visually, okay? We're going to do this visually. So we need to know how those pi orbitals look. And so I did this in one of my previous videos. I showed you guys how these look. Right, there's a representation here, right? They kind of look like p orbitals, and they are both orthogonal, right? So there's one that's 90 degrees from each other, there's 2 that are 90 degrees from each other, okay? So I'm going to take this idea and kind of bring it back down to where we were before. So scrolly, 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 all right. And then we'll zoom in a bit, okay? And so let's say we've got our oxygen molecule here, right? It's bound to another oxygen molecule here. Our pi star orbitals are going to look something like this. I'm going to just do them in red and blue to maybe make this a little bit easier for you guys, okay? I'm just going to arbitrarily shade the blue ones in and leave the red ones. So that doesn't really matter, right? So this is one of our pi star orbitals, okay? The other pi star orbital, all right, let me let me try and draw this one. The other pi star orbital is going to be 90 degrees from this one, right? So imagine if you rotate this 90 degrees, right? So that the orbitals are coming into and out of the plane of the board, right? So we basically would see just a giant lobe in the front here, okay? And then we would have the other lobe kind of hanging out in the back. And we would have the other, whoops, that wouldn't be shaded in, pardon me, got a little bit ahead of myself. And then we would have the other lobe here in the back. Man, look, I don't want to brag too long, but, you know, that's some serious artistry skills right there, okay? I'm joking, those suck. All right. So, here's the thing that we would do if this was in reality, right? In reality, what we would do is we would go through and figure out the symmetry for all these different orbital sets, right? We would look it up and they would be, you know, we would find that maybe they might be, you know, B1 or T1U or EG, right? All those different things that we could pull out of the point group tables. Now, we did not talk about point group tables in this course, right? So I'm trying to avoid that as much as possible, but when you go to look this stuff up, you'll start to see some labels for these different systems, right? And remember, once we find those different labels, then we can just play the matching game, okay? So by symmetry, the pi star orbitals have the same, or can overlap with the dz squared, and they're going to overlap with the xz orbitals here, okay? The xz or the yz, it doesn't really matter all that much, right? So here's how this is going to look. Let's try and take a visual depiction of this, okay? So here's my iron center, okay? Let me draw my z squared orbital, right? Z squared looks like this, and then we got the donut around there, okay? Let me do the donut in blue because it is the opposite phase, right? So, right, we got the donut in the blue, that's kind of around there. I just put an F there, excuse me, that should be an FE, right? So let's think about this for just a second, right? We really got to think about this. So let me pause here for just a second. There's my dz squared orbital. Now, what's going on? Well, my dz squared orbital, remember, is my donut is on the plane where my porphyrin, okay, where my porphyrin is binding, right, to that donut, okay? So the porphyrin is in the plane of the donut. Down here at the bottom, right, here's where my other histidine is, okay? So a lot of this is involved with the bonding, right? But remember, when we're dealing with the metal orbitals here, the dz squared, right, this is our anti-bonding orbital, right? But who cares? That's not that important. What is important is that we actually have an open lobe right here on our dz squared orbital. So what we're going to do is bring in our pi star orbital here, right? So let me see if I can draw this as best I can. My oxygen is going to come in bent, right? Let me move this over just a bit here. So one lobe, pi star, right? Blue and blue. You guys with me on this? Remember, for a bond to happen, the orbitals have to overlap in a head-on collision. So if I bring in my oxygen bent, right, I can overlap my pi star with my dz squared orbital. As opposed to, if I bring this in a linear fashion, okay, I'm just going to redraw this real quick. If I bring this, whoops, that should be red. If I bring this in a linear fashion, okay, here's my oxygen, red, blue, right? There's my other oxygen, red, and blue, okay? If I try and bring this on like this, right, there's no orbital to overlap right here. So the dz squared won't be able to interact with that. Now, we could interact, in theory, with a couple other orbitals. But what we would end up doing in a linear fashion, if we try to bring in the oxygen in a linear fashion, at best we could only make 2 pi-type bonds. Okay? So if we bring in the oxygen in a linear fashion, the best we could make is 2 pi-type bonds. As opposed to if we bring this on bent, right? What we're just depicting here is 1 sigma bond, okay? Now, a sigma bond is a pretty darn strong bond. It's a good interaction, right? And you're saying, well, wait a minute, do we really want a good interaction, right? Do we want... Well, the answer is yes, because we do want to bind this oxygen and then take it to somewhere else, right? So we can't have a super-duper weak bond, but we also don't want a super-duper strong bond, right? So this is a pretty... We're asking a lot here, but this is, this is the way it works, right? We are making a sigma-type bond using one of our pi star orbitals, okay? And I will try my darndest to draw what's going on here for you guys, okay? So I'm going to take a quick pause to draw this, and we're going to see if we can figure out the interaction here with this other pi star orbital, okay? So, all right. Ta-da! Again, far be it for me to take the next 30 minutes to brag about my artistic mastery, but there it is. Okay, right. So let me see if I can, break this down a bit. Okay. So just for our argument's sake, right? Let's put in a Cartesian set of coordinates here, right? And we'll call this x and we'll call this y, right? So we are dealing with the yz orbital, although in theory we could swap the x and the y also. Okay. Now I want you guys to note something here. Okay. I'm going to scroll back up. Right. So you guys see I still have the porphyrin ring. Right. If we're bringing in the oxygen here to make a sigma bond, we can't change the orientation of that. Right. We can't magically rotate the oxygen, then use a different set of orbitals, right? Once we kind of fix something in position, then we just have to deal with the way that it is in that position, okay? I hope that kind of made sense, right? This is pretty darn tricky to visualize. This is I'll be honest, this is pretty high-level stuff, right? This is things that I talked about in graduate school after I've had, almost 2 semesters of inorganic chemistry. So if you guys are looking at it and saying, what in the world is this dude talking about? I know it's kind of tough, right? But I've got some pictures for you guys, and, I'll post a link to some stuff for you guys too, okay? But what we have here is a pi-type interaction. Okay? And that's really the kicker here. If we bring in the oxygen in a side-on manner, we can make a pi-type and a sigma-type interaction. And that's going to be extremely useful for us. Okay? Because the name of the game is, right, we want to be able to bind that oxygen to this iron center. And if we bind oxygen in this bent end-on manner, okay, we can make a sigma bond and a pi-type interaction. And that's a good thing, right? Those are positive things that encourage the oxygen to want to bind in this bent manner, as opposed to the linear or the end-on, which is the other 2 options. Now, your immediate question should be, who cares and so what? Well, here's the point. So right now, as you guys have been listening to me for the last 14 minutes, okay, you guys have been breathing in and out, right? I know, right? I can tell you guys are shocked, right? I've been breathing. Okay, so the point being, what are you guys breathing in, right? You guys are breathing in a lot, mostly a mixture of oxygen and nitrogen, okay? And the thought should be, well, why is oxygen selectively binding to the iron? And there are basically 2 big reasons for it. And these are 2 big reasons, okay? Selectively I'll just abbreviate Hg for hemoglobin there, right? Because we've got a lot of oxygen, there's probably even some CO2, right? There's a lot of that in my office as I sit here and yammer on to you guys. How is my hemoglobin essentially filtering out everything but just binding oxygen? And the answer to that, right, I said there are two smart answers. There's a steric answer and there's an electronic answer. What we're dealing with right now is the electronic answer. Nitrogen, N2, cannot bind in this bent end-on manner, okay? The reason for it, just in brief, is because well, let me see if I can put it this way. The orbitals in nitrogen are at a very different energy level, and they will not want to bind in this manner. Plus, right, they're going to be filled orbitals and unfilled orbitals, aka the electrons are going to be in a different position, which means that nitrogen could, in theory, only bind in a linear fashion. Okay? It could bind in a linear fashion, but it's not going to. Okay? So nitrogen is excluded by sterics and electronics. Okay? We could ask the question about carbon monoxide. Okay? Now we know that carbon monoxide will, right? Carbon monoxide will kill us, right? Because it irreversibly binds to hemoglobin at standard conditions. Hemoglobin only can bind in a linear fashion. Now, it binds in a linear fashion in such a good way, right, that it overcomes any of the steric problems. Now, what do I mean by sterics here in this case? Excuse me, I just had something drop on my screen here. Now, remember, we kind of did a visual depiction of this last time. Maybe I can just scroll up here then. Oh yeah, this looks good, okay? Remember that hemoglobin here, right, is kind of bound near the edge of the individual portion of hemoglobin. And we've got this histidine that's sitting up there. When oxygen comes in, it'll bind in this bent end-on manner. And there's theory that the imidazole helps stabilize that, and I don't think we're going to get to that directly in this course, right? But think about it like this. Let's say that oxygen tried to bind in a linear fashion. Uh-oh, right? Anything that tries to bind in a linear fashion to hemoglobin, there's going to be a steric problem wherein whatever it might be, the oxygen or the nitrogen or the carbon monoxide or any of these other things, it's going to start to sterically interact with that imidazole that's sitting above the iron center. Okay? So there's a steric hindrance in the sense of that something is sterically blocking a linear binding manner. Now, that doesn't mean that carbon monoxide can't overcome that, because it will, right? If there's enough carbon monoxide around, it will bind to your, hemoglobin, and then oxygen can't come in, right? It's really hard to displace carbon monoxide. I believe the only treatment they really have is to put you guys basically in a hyperbaric, in a hyperbaric chamber and kind of, increase the pressure of O2, right? But, I'm also not a medical doctor, right? So maybe some of you guys can correct me on that. But anyway, there's a steric and electronic argument as to why things want to bind in only a bent end-on manner there, okay? And that's important to recognize. That histidine that's up here has a very important role, okay? But anyway, let's try and summarize this, okay? Here are the two binding modes, right? Here are the two visual depictions of how oxygen will bind to the metal center, okay? It'll bind in a sigma-type interaction between the pi star, right? Remember, this is our pi star orbital on the O2, and the dz squared, right? Dz squared on the metal. And then the other pi star interaction will interact with either the xz or the yz. By convention, we say the xz orbital, but it doesn't really matter, right? Either way is just fine. It interacts with one of the pi-type orbitals, the pi-type d orbitals in the z-axis, right? That's what we should really say with this, okay? So this, in effect, makes a good bond between a bent end-on oxygen molecule, right? And kind of prevents electronically, or not prevents, I should say, it discourages linear binding to the metal center, okay? All right, you guys might have to watch this video more than once, okay? That's fine. This is tricky stuff. Now, I'm going to switch over here for just a second. These are, I don't know why this keeps highlighting, stupid thing. Okay, these are my notes from when I was taking this course. So this is all thanks to Dr. Christou, okay? At the University of Florida, okay? So I am not taking credits for any of this stuff. These are his notes. So please, if you find this helpful, you can drop him an email. And he's a very busy guy. I mean, don't spam him. But if you do find this useful, right? These are I posted these for you guys online, but these are Dr. Christou's notes, and he took a lot of time kind of putting these together. And I hope they're useful for you guys too, right? But you can see he's a much better artist than I am. He kind of shows the complete MO diagram for you guys here, and he goes into far more detail. And you can even, right, if you're interested, you can even see my scribblings and musings as I was taking the course from Dr. Christou here. So there's a lot of information in here, right, and you guys can go through this and kind of read through it and kind of give you guys a better idea. But the important part that I want to talk to you guys about, or the point that I wanted to make, is that there is both an electronic and a steric argument as to how oxygen binds to a hemoglobin center, okay? The shape of things is important. Now, you guys already knew that, otherwise I wouldn't have spent all this time talking to you guys about geometries and MO diagrams and all this other kind of stuff, okay? All right, so next time what we'll do is we'll talk about what happens at the metal center, okay? So now that we know what happens to the oxygen and why it happens, what we'll talk about next is what happens at the metal center when oxygen comes in.